This is the solution for question number 8 for dynamical systems and chaos. Question 8a asks you to write a short MATLAB program to plot a multifractal spectra for the Cantor set. And part B, again, is related to the Ikeda map. And we want to determine fixed points of period 1 for this Ikeda map. So for part A, we just have to remember the code in order to plot an F alpha curve. We're given the formulae for alpha S minus Fs. So those will appear here. So we start with K is 500. Here are our values for P1 and P2 when constructing the multifractal Cantor set. So P1 is 1/6, P2 is 5/6, and we want to leave these as fractions, so we use the sim command. The parameter T is our S, so T is going to go from 0 to 500. So here is X, the formula for X, which is given by the alpha. And then we have a little for loop here. We have our log, so here is the formula. So capital Y here refers to the F. So it's log K choose T. So K choose T divided by K log 1/3 is the same as minus K log 3. And then in the exam, you don't have to put these labels on. So I've just done this to make it look pretty. So here's the alpha axis, here's the F alpha axis. But as I said, you only need these few lines of code up here to plot the F alpha curve. I've also plotted this line here just to show that it is tangential. But again, in the exam, you do not need to plot that line. You also asked, what information does the local maximum give? Remember, this local maximum gives a measure of density. So this is the fractal dimension of the object, and that gives a measure of density. For part B, here is the Ikeda map, and we want to determine the fixed points of period 1. So we have to split this into real and imaginary parts. So we set xn plus 1 equals xn equals x, yn plus 1 equals yn equals y. So xn is the real part of en, yn is the imaginary part of en. Again, we use Euler's formula, so we get a formula for x and y, and then we can use easy plot to plot both of these implicit curves. Now again, in the exam, you can use different colours, but you won't lose marks for not choosing different colours. I've given you examples like this in the course. So this is what we get if we easy plot these two implicit curves, and you can quite clearly see that there is one fixed point. We then use the data cursor in MATLAB. So use the data cursor to locate this point, and you can see it's roughly here. So there's only one fixed point. The next thing to do is determine the stability of that fixed point. So we have to use the Jacobian matrix, which I haven't given you here. So for a bit of practice, I want you to find the Jacobian. So J is, so here's our P. So we take dp dx, and then dp dy, and dq dx, and dq dy, etc. And then we can use MATLAB to find the eigenvalues. And I've given you the answers here. So the eigenvalues for this one fixed point are given here, and because the modulus of these eigenvalues are both less than 1, then this is a stable fixed point. So this single fixed point is stable. And as I said, we have done a few examples like this in class. And this concludes the solutions for question number 8.